cubic, we've done body-centered cubic. Now we're going to get to face-centered cubic structures. So again, very important structure for nickel, copper, calcium, describes a lot of different materials. But face-centered cubic is a little bit different from the other ones, and it's kind of denoted by its name, face-centered cubic. So there's going to be atoms at the corners, as always, from our structure. There's also going to be these atoms at the faces. So I'm going to draw them as black here. So there are atoms right at the face of each of our 6 sides of that cube. So let's go ahead, we can describe again and kind of look at the structure. So now, similar to body-centered cubic, when we look at our PowerPoint slides, so here we saw a gap between those kind of our corner atoms here from our body-centered cubic. And we'll see something very similar from our face-centered cubic now. And you can also see, look at the nearest neighbor distance. It's not here. The nearest neighbors are from here to the face. So our origin atom, or corner atoms, to each of the atoms on the face. So if I was looking at this atom, for example, my nearest neighbor distance would be this guy, 1, 2, and then it'd be on the other kind of side anyways. But you could kind of see the picture, or get the picture here. So I'm looking at this atom. My nearest neighbors are 1, 2, and 3 right there. So you can see actually a larger distance here. So we saw that A was equal to 2R for simple cubic. We saw that A was equal to 4R over 3 for BCC. And you can see that this gap's going to get a little bit bigger because we have this atom at the face. So let's go ahead and look at our structure. Values. Let me discard the ink notation. Back to kind of our notes here. So let's answer one of the first questions we typically answer, which is, again, you could describe these kind of our primitive lattice vectors, as we've kind of done previously. Let me show here. And how many atoms are going to be in an FCC unit cell? Well, again, we know that each of these corner atoms is an 8th, and they're 8 of them. For BCC, we saw that they were inside the structure, but here they're just at the face, right? These atoms here are kind of, again, at the face of the cell. So really, they're going to be a unit cell on top of this one. And that's really all the other unit cells that it's going to share. So if it's on the face, this atom here, all these atoms that are face, they're going to count as a half. And how many atoms do I have here? 1, 2, 3, 4, 5, 6. I have 6 atoms here. So that's going to lead to 4 atoms in my FCC unit cell. What's my nearest neighbor distance? Well, again, it's this distance right here, right? So we know that this is 2R. And we also know that this is going to be 2R as well. So that's going to give us a value. So our nearest neighbor distance is equal to 2R. Can never be greater than 2R. Always 2R. How many number of nearest neighbors we have? Well, that's actually a little bit more kind of complicated to get at, and you have to kind of imagine that in 3 dimensions. So you could see here, for example, this guy, we have 1, 2, 3 nearest neighbors, and then you're going to share it, going in the kind of 3 dimensions. So for FCC, we have 12 nearest neighbors. And again, you can look at the Mathematica notebook and kind of try to visualize that. But there's 12 nearest neighbors for our FCC structure. So 4 atoms, 4 nearest neighbors. Next nearest neighbors, don't have to worry about it. Nearest neighbor distance, 2R. What is our lattice parameter here? So let's go ahead and again draw out the structure. So I'm going to draw out my FCC structure. I'm going to draw the atoms in a different color this time, just so we have some perspective. Here, 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 and then here. It's kind of difficult to draw that structure. But anyways, so let's look, for example, I don't know why I draw that one. I don't know why I draw this atom at the origin here, so huge. But what is this distance here? So, this is A, this is A. What is this distance? Well, I know that from this atom, this is my nearest neighbor, and from this atom, this is also my nearest neighbor. This distance is 4R. So if I want to find A, now it's A squared plus A squared equals 4R squared. Let's go ahead and calculate that out, although I think that hopefully people will use Mathematica just in case. So let's go ahead and solve. A squared plus A squared equals 4 times R squared. over A. So it's 2 root 2r. So let's go ahead and write that one down. So our next nearest neighbor distance, or our A parameter, A is equal to 2 root 2r. Just like that. Excellent. And now finally, what do we need to do? Let's calculate our atomic packing factor, our APF. So if I have an atom, or actually a cell like this, we know that our APF function is going to be equal to how many atoms? 4 times 4/3 pi r cubed divided by A cubed, where A is equal to 2 root 2r. Now, so let's see if this is a closed factor. So I'm going to go ahead and do 4 times 4/3 times pi times r cubed. Let's put that in parentheses, divided by 2 square root 2 r cubed. And actually, I'm going to put that in parentheses too, just so we don't have any issues. Let's evaluate that numerically, and we get our 0.74 number. So we see that our atomic packing factor number here is 0.74. So this is APF. This is the maximum possible packing factor for spheres having all the same diameter, the same size. So this is, in fact, a close packed structure. So this is FCC is close packed. And we're going to see the implications. If your structure is close packed, you will have here a close packed plane. So we're going to get into that. So this is FCC. So in the next video, we'll kind of do a quick little summary. But before we get into that, hexagonal close packed, as his name kind of identifies or kind of tells you, is a close packed structure as well. HCP is a very important structure for titanium, zirconium, yttrium. And we're going to actually have kind of this different type of basis. So it's this hexagonal basis. And actually, you can kind of, if you take a more in-depth structure class, you'll kind of go through all these values. But for hexagonal close packed structures, we have 12 nearest neighbors again. Our distances are 2r for the nearest numbers. And if you look at the atomic packing factor, it is 0.74 again. And you'll have actually this C to A ratio differs for different materials. But anyways, that's a little bit beyond the point. But the key thing here is that HCP, close packed structures. And that's going to, again, make them more ductile. It's going to be easier for dislocations to move in close packed structures along close packed planes and along close packed directions. So that's kind of the key factor there. So they are both same packing factors, same atomic packing factors. They are close packed structures. They have the maximum packing density of this value here. And you can also distinguish them. FCC, if you look at these planes of atoms, they stack as A, B, C indefinitely. But HCP will stack as A, B, A. And actually, when you have defects, which we're going to get into in lecture 3, but you might have these stacking fault defects. Or which have stacking fault energies, SFEs. But anyways, you basically get something that stacks like this: A, B, C, A, B, B. So that's a stacking fault defect. But anyways, so you can kind of see the difference between how HCP structures look versus FCC structures look. So you'll get these kind of difference in these tetrahedral sites and octahedral sites. We kind of mentioned that in the previous video. Tetrahedral sites, you have these 4 nearest neighbors. Octahedral will have 6. Very important in ceramics, again. So these close packed planes, close packed directions, we're going to get into that in the next video, or the video after the next video. So we'll get into that in just a bit, but only, actually we'll get more into detail of that. So FCC is ABC, HCP is ABA. So that is essentially it for our structures. What we'll do in the next video, we'll have kind of a little summary lecture, but yeah, that is your cubic structure. So be ready to kind of answer some of those questions. So thanks. I'll see you all in the next video.